Now in this video, we're going to be talking about thermal expansivity. Now this has to do with the change in the size of an object due to the application of heat. Now when heated, most solids and liquids expand. They also contract when cooled. This expansion or contraction can either be in length, we call it linear expansivity, area, we call it area expansivity, and also volume, we call it volume or cubic expansivity. Now the linear expansivity, okay, can be defined as the increase in length per unit length per degree rise in temperature. Linear expansivity of a substance is defined as the increase in length per unit length per degree rise in temperature, and it is represented with the symbol alpha and is measured in per Kelvin or per degree Celsius. Mathematically, we have linear expansivity to be equal to change in length all over the original length times change in temperature. So we have L2 minus L1 all over L1 times change in temperature, where L2 minus L1 is simply the change in length, L1 is the original length, and this is the change in temperature. This is called linear expansivity. You can see it here stated. Alpha is linear expansivity, L1 is the original length, L2 is our final length after expansion, Theta 1 is the initial temperature before expansion, theta 2 is the final temperature after expansion, and delta L is the change in length. Delta theta is the change in temperature. So let's see an example of a question where this can be applied. In this question, they said a bridge made of steel is 600 meter long. So we have original length to be 600 meter. They say what is the daily variation in its length if the nighttime and daytime temperature are, so we have initial temperature to be 10 degrees Celsius, all right, nighttime and daytime, all right, new temperature to be 35 degrees Celsius. They take the linear expansivity of steel to be 0.00012 degrees per degree Celsius. All right, so now we go straight to our equation for linear expansivity, which is alpha equals, what are we looking for? The daily variation, that's the change in length. Daily variation in length, so we're looking for the change in length. So we have delta L, don't forget, all over L1, all right, times delta theta. That's the change in temperature. And our change in temperature is final temperature minus initial temperature. 35 minus 10, which is 25 degrees Celsius. So we're going to have 0.00011012 equals the change in length, daily variation in length, which is what we're looking for, all over the original length, which is 600, times the change in temperature, which is 25. Okay, so simplifying further, we can cross multiply change in length times 1 equals change in length equals this times this times this. So we have 0.000012 times 600 times 25. So our change in length now is going to be, we use our calculator here, 0.00012 times 600 times 25. That will give us 0.18 meter. Okay, this is in meter, 600 meters. So now to get the change in length in cm, we'll simply multiply it by 100. Okay, so we have the change in length to be 0.18 times 100, which is 18 cm. That's option C. Now the next one we're going to be talking about is the area expansivity and volume expansivity. Now the area expansivity, also known as the superficial expansivity, is the increase in area per unit area per degree rise in temperature. That change in area on application of it is what we call area expansivity, and the symbol is beta. And mathematically, area expansivity equals change in area expansivity beta equals change in area all over the initial area times the change in temperature. Final area minus initial area all over original area times final temperature times initial temperature. The whole of this can be simplified to change in area all over original area times change in temperature. So this is what we have here. Now we also have that area expansivity is equal to 2 times linear expansivity. Alright, so this is linear expansivity. 2 times linear expansivity will give you area expansivity. Now, talking about the volume expansivity, also known as cubic expansivity, is the increase in volume of a substance per unit volume per degree rise in temperature. Just like we have area expansivity to be increase in area, volume expansivity is increase in volume on application of it. So it is represented with the symbol gamma. And mathematically, volume expansivity is change in volume all over original volume times change in temperature. Alright, you can see it listed here. This is gamma is volume expansivity, original volume before expansion, final volume after expansion, initial temperature, final temperature, change in volume, change in temperature. Now also take note that volume expansivity is 3 times linear expansivity, just like we have area expansivity to be equal to 2 times linear expansivity. We have that volume is equal to 3 times linear expansivity. Now looking at this question, it says the area expansivity of a metal is 4.8 times 10 raised to power minus 7 per Kelvin. So we have beta given to us to be 4.8 times 10 raised to power of minus 7 per Kelvin. It says determine the linear expansivity. What's the relationship between these two? We know that area expansivity is equal to 2 times linear expansivity. So to get linear expansivity, we divide both sides by 2, and that will give us linear expansivity to be equal to area expansivity all over 2. So area expansivity was given in this question. We have 4.8 times 10 raised to the power of minus 7 all over 2. Okay, that will give us 2.4 times 10 raised to the power of minus 7 per Kelvin, which is option C. Now moving on, here they say the linear expansivity of brass. So we have alpha to be equal to 2 times 10 raised to the power minus 5 per degree Celsius. Alright, the linear expansivity of brass is this. They say if the volume of a piece of brass is this at this, so we have initial volume to be 15 cm cube at this temperature, initial temperature to be 0 degrees Celsius. So what is the volume at 100 degrees Celsius? So we are looking for V2, alright, at a new temperature 100 degrees Celsius. Okay, so how do we go about this question? Volume, change in volume is accompanied by volume expansivity. So this is supposed to be volume expansivity equals change in volume V2 minus V1 all over original volume times change in temperature. But what they give to us here is linear expansivity, not volume expansivity. So we need to convert this linear expansivity to volume expansivity before we can use it in this formula. We cannot use linear expansivity with change in volume. No, that's wrong. We use volume expansivity with change in volume. Alright, so first we need to convert this linear expansivity to volume expansivity. Now recall, we said volume expansivity is equal to 3 times linear expansivity. So we're going to have this equals 3 times, we have 2 multiplied by 10 raised to the power of minus 5. And that will give us 2 times 10 raised to the power of minus 5. And that will give us 6 times 10 raised to the power of minus 5. All right, so that's what we're going to use in our equation here. So come down here, we're looking for the new volume. All right, so come back to our equation. We have 6 times 10 raised to the power of minus 5 equals V2, which is unknown, minus initial volume, which is 15, all over 15 times the change in temperature. All right, change in temperature, final temperature minus original temperature. So we have 100 minus 0, that will give us 100. All right, so simplifying, we're going to cross multiply V2 minus 15 times 1, that will give us V2 minus 15 equals this times this, that will give us 6 times 10 raised to the power minus 5 times 15 times 100. All right, so that will give us V2 minus 15 equals this times 100. We have 6 times 10 raised to the power minus 5 times 15 times 100. That will give us 0.09. So we have 0.09. So V2, moving minus 15 to this other side of the equation, that will give us 0.09 plus 15. And that will give us, will be equal to 15.09 cm cube. All right, so this is the new volume, which is option C. All right, so with this, we've come to the end of this video. Please subscribe to this channel, drop a comment, and make sure you like this video, and also share it to your friends and your colleagues.